Good morning, good afternoon, and good evening wherever you are. I'm Vanessa Tan, and I will be presenting our research entitled MATA-RL, Continuous Reaction Wheel Attitude Control using the MATA simulation software and reinforcement learning. As Earth observation satellites, there's a need to have a high degree of target pointing accuracy. However, Diwata satellites have low orbits and would experience relatively strong external disturbances. Satellite operators would need to determine the optimal parameters and commands for accurate target pointing. Current methods for attitude control have proven to be effective. However, they are prone to changes in control and mass parameters. A sudden change in these parameters caused by the deployment of a solar panel or other unpredictable disturbances would result in inaccurate attitude. With the rise in popularity of using machine learning in autonomous control, we explore an attitude controller using deep reinforcement learning. This research presents three main contributions. First is the implementation of two deep reinforcement learning algorithms for continuous attitude control using the reaction wheel speed as action space. Second, we extend the Diwata simulator, MATA, as a training environment for our satellite agent. And finally, we compare Diwata's current controller, the PID, with implemented RL algorithms. The rest of this presentation is divided into four parts. I'll briefly discuss the spacecraft kinematics and dynamics and the reinforcement learning algorithms, and I will be presenting the results and case studies. And lastly, the conclusion and future work. The satellite dynamics can be simulated using the first equation. This rigid body equation, stemming from the law of angular momentum, determines the satellite's angular acceleration from the control torque and external disturbances, such as the gravity gradient and atmospheric drag. On the other hand, the second equation shows the satellite kinematics. The rotation values of the satellite attitude are represented as quaternions. The control torque is calculated by the satellite's processing unit and are enforced by actuators such as reaction wheels, as shown in this image. The speed and mechanical alignment of each reaction wheel is ultimately translated to the spacecraft's control torque. The PID, or the proportional integral differential control, whose general form is shown in this slide, is traditionally used by small satellites such as Diwata. This controller depends on the difference between the target and current attitude values. The tuning of the PID scale values is essential to get a good response. The PID parameters, or the gain values for a certain condition, will not necessarily work with others. Please check our paper for more details of the satellite kinematics, dynamics, and control. And let's discuss an overview of reinforcement learning. Reinforcement learning has 5 components. So we have here the agent, the learner, and decision maker. And if we translate it to a Mario game, it would be Mario. And then the environment would be Mario's world. And then the action would be up, down, left, and right. And the state of the agent would be the current position of Mario, and if Mario powered up. And then the reward will be the coins that Mario gathered. And if he finished the episode, he will be given a much greater reward. So if we translate those concepts to the satellite attitude control, our agent would be the satellite, and then our environment would be the MATA simulator. And then our states, we have 3 states, the error quaternion, and then the rotation rates, WBI, WBR. WBI is the rotation rate with respect to the inertial frame, and WBR is the rotation rate with respect to the reference frame. The reward is dependent on the target error angle and rotation rate. I will be discussing in detail the reward function in the next slide. And then lastly, our action space will be the 4 reaction wheel speeds of our Diwata satellites. The reward function consists of 2 components. We have the quaternion reward and the rotation rate reward. They are exponential functions which give the agent more rewards when it's near the target. The total reward is their product, which would help the agent maximize the reward and make sure that the target quaternion and rotation rate are achieved at the same time. The agent is given an additional reward when the error quaternion is less than 0.1 degrees, which makes sure that the satellite stays on target during the pass. Two algorithms implemented in this research are policy gradient actor-critic methods. A policy gradient method explicitly updates the policy in every time step. The critic updates the value functions, which tells you how good the action is. The actor then updates the policy in the direction calculated by the critic. So the two actor-critic algorithms is the PPO and SAC. So the PPO is a Proximal Policy Optimization. It is an on-policy algorithm which updates the policy in real time. It is effective for UAV attitude control and it is computationally simplistic. And then on the other hand, we have the SAC for the Soft Actor-Critic. It is an off-policy algorithm which reuses previously collected data, or it has a memory buffer. With this characteristic, SAC is sample efficient and can maximize the entropy of the policy. With high entropy, the agent is encouraged to do more explorations. Here are the training results. So we have here the orange line for the SAC and the blue line for the PPO. So the SAC algorithm achieved a higher cumulative reward than the PPO. SAC reached convergence around 15 million steps, while the PPO needed 30 million steps to achieve convergence. A future work in training RL algorithms for attitude control is the exploration of other observation states. A reduction of observation states could also improve the cumulative reward and achieve faster convergence. Here are demos of the two algorithms. We can see that SAC reached the target faster than the PPO. To test the control performance of the agent, different scenarios were simulated using the Mata simulator. In these case studies, we compared a PID controller with the RL algorithms. The first scenario is the Diwata to stalled configuration. This would be the baseline, since this was used during training. Here is the control performance for the attitude angles. It is represented as the roll pitch yaw. The algorithm which achieved the fastest settling time is the SAC. On the other hand, the worst performing algorithm is the PPO. And here is the control performance for our rotation rates. The PID achieved the smallest overshoot and is the most stable. On the other hand, SAC is still the fastest attitude controller. The second scenario is the Diwata to deployed configuration. The simulation would test the performance of the attitude controllers against disturbances and changes in inertial matrix. We trigger the deployment at a 300-second mark. Here is the control performance for the attitude angles. An interesting result for this configuration is at 300 seconds deployment time, the PPO did not have an overshoot compared to the PID and the SAC. Here are the results for the rotation rates. The PID is the most stable after deployment. And consistent with the attitude angles, the PPO has the smallest overshoot for the rotation rates. Hence, it is the most robust to sudden disturbances. The last scenario is a demonstration how the attitude controllers can still perform even if they are evaluated in a different satellite. The PID controller for this scenario was retuned for the LM50 satellite. LM50 has a different flight heritage and mass parameters with Diwata too. So for the results of the LM50 satellite, SAC is still the fastest algorithm and it has the smallest overshoot. With the same behavior as the attitude angles, SAC achieved the fastest settling time and smallest overshoot for the controlled performance of the rotation rates. Even though we did not retune the RL algorithms, SAC still performed well or even better than the PID. So here is a summary of the different case studies. SAC is the fastest attitude controller when no sudden disturbances occur. It is also comparable with the PID controller in terms of the stability and overshoot metrics. PPO has the worst performing metrics, however, it is the most resilient to sudden disturbances. The case studies only showed scenarios with fixed initial and target parameters. To get a general overview of the performance of the attitude controllers, an additional evaluation was implemented. For the overall evaluation, the Diwata 2 stowed configuration was utilized. The initial state and target parameters were randomized for each episode, and we evaluated this for 5,000 episodes. So here is the overall results. So for the box plots, same colored box plots indicate that the metrics are not statistically significant. It can be seen that the SAC and PID controllers are comparable in terms of achieving the minimum error angle, and SAC is the fastest to converge in terms of achieving the minimum error angle. For the rotation rates, SAC achieved the lowest rotation rate. It is also the fastest to converge. The results also show that the PID and PPO are comparable in terms of the time the rotation rate reaches its minimum. Please check our paper for more details for our results. To summarize, this research demonstrates two reinforcement learning algorithms for satellite attitude control. The results show that the RL algorithms can outperform the traditional controller. There are different criteria in choosing which RL algorithm fits the intended attitude control. If the priority of the satellite is to be robust in sudden disturbances, the best algorithm is the PPO. For fast attitude target, the best algorithm is the SAC. It is also the most comparable algorithm with the PID in terms of stability. Should also note, even without retuning the RL algorithms, they gave a good response. RL algorithms with the combined features of PPO and SAC can be explored for future work. We would also want to explore algorithms without reward engineering. Reward functions vary in different works for attitude control. If the agent could predict without relying on a reward function, a more generalized satellite agent can be developed. We would also investigate how to implement and test these RL algorithms in an engineering model. Thank you, that will be the end of my presentation.